Tonight, we're going to explore something that seems simple, but will completely rewire how you understand reality. Why is the speed of light the ultimate limit? You've probably heard that nothing can travel faster than light. But here's what almost nobody realizes. This isn't about light at all. Light doesn't own this speed. The universe does. The speed of light is actually the speed of causality itself, woven into the very fabric of space-time. And Richard Feynman, perhaps the greatest physicist of the 20th century, saw something about this that most people completely miss. What he uncovered wasn't just about physics. It was about why the universe can even exist, why cause can lead to effect, why reality makes sense at all. And once you understand it, nothing looks the same. Before we dive in, if you find this kind of deep exploration fascinating, a quick like or subscribe would really help this channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that seems straightforward. Light travels fast. Really fast. About 299,792 kilometers per second to be precise. That's roughly 186,000 miles per second. In 1 second, light can circle the Earth about 7.5 times. It can travel from the Earth to the Moon in about 1.3 seconds. From the Sun to the Earth in about 8 minutes and 20 seconds. To put this in perspective, imagine you could somehow travel at the speed of light. You could circumnavigate the entire planet before you finished reading this sentence. You could reach the moon faster than it takes to brew a cup of coffee. You could travel from New York to Los Angeles and back over 40 times in a single heartbeat. This speed is so far beyond anything in human experience that our brains struggle to comprehend it. This speed is so extreme that for most of human history, people assumed light traveled instantaneously. You open your eyes and you see things. There's no perceptible delay. The room just appears. When you flip a light switch, the darkness vanishes immediately. When lightning strikes on the horizon, you see the flash the instant it happens. Ancient philosophers debated whether vision worked by light coming into the eye or by something going out from the eye. But almost everyone agreed that whatever was happening, it happened instantly. The Greek philosopher Empedocles, around 450 years before the Common Era, suggested that light might take time to travel, but Aristotle dismissed this idea. He argued that light was not a thing that moved, but rather a state of the transparent medium between objects. For Aristotle, light didn't travel at all. It simply was, like the color of a wall or the hardness of a stone. For nearly 2,000 years, Aristotle's view dominated Western thinking. Light was instantaneous. Distance didn't matter. When you looked at a mountain miles away, you saw it as it was right now, not as it was moments ago. The idea that light had a speed, that it took time to cross distances, seemed absurd. The first person to seriously challenge this assumption was a Danish astronomer named Ole Rømer in 1676. Rømer was working at the Royal Observatory in Paris, studying the moons of Jupiter. Jupiter has many moons, but the 4 largest, discovered by Galileo in 1610, are easily visible through even modest telescopes. Rømer was particularly interested in Io, the innermost of these large moons, which orbits Jupiter every 42.5 hours or so. Astronomers used Io's eclipses as a kind of celestial clock. When Io disappeared behind Jupiter, blocked from view by the giant planet, that moment could be predicted and timed precisely. Or so they thought. Rømer noticed something strange. The timing of Eo's eclipses varied depending on where Earth was in its orbit around the Sun. When Earth was on the same side of the Sun as Jupiter, moving closer to the giant planet in its orbit, the eclipses happened earlier than predicted. When Earth was on the opposite side, moving away from Jupiter, they happened later. The difference wasn't huge, about 22 minutes over the course of half a year, but it was consistent and measurable. Römer realized what was happening. Light from Jupiter's system was taking different amounts of time to reach Earth, depending on the distance. When Earth was closer to Jupiter, the light had less distance to cover, so Io's eclipses appeared to happen earlier. When Earth was farther from Jupiter, the light had more distance to cover, so the eclipses appeared to happen later. The variation in eclipse timing wasn't a problem with the predictions. It was a measurement of light's travel time. From these observations, Römer calculated that light took about 22 minutes to cross the diameter of Earth's orbit, a distance of roughly 300 million kilometers. This gave a speed of about 214,000 kilometers per second. His estimate wasn't perfectly accurate because he didn't know the exact size of Earth's orbit, and his timing measurements had some uncertainty. But he had proven the crucial point. Light has a finite speed. It takes time to travel from one place to another. This was revolutionary. It meant that when you look at a distant star, you're not seeing it as it is now. You're seeing it as it was years or even centuries ago, however long it took the light to reach you. The universe suddenly had a temporal depth that no one had imagined. Looking out into space meant looking back into time. Over the following centuries, scientists developed increasingly precise methods to measure light speed. In 1849, the French physicist Hippolyte Fizeau devised an ingenious terrestrial experiment. He used a rotating toothed wheel and a mirror placed several kilometers away. Light would pass through a gap in the wheel, travel to the mirror, bounce back, and either pass through another gap or be blocked by a tooth, depending on how fast the wheel was spinning. By carefully adjusting the wheel's rotation speed, Fizeau found the point where the returning light was completely blocked. At this speed, the wheel had rotated exactly enough for a tooth to move into the path of the returning light during the time the light traveled to the mirror and back. Knowing the distance to the mirror and the rotation speed of the wheel, Fizeau calculated the speed of light to within about 5% of the true value. It was the first successful measurement of light speed using equipment entirely on Earth's surface. In 1862, Léon Foucault improved on this with a rotating mirror method, getting even closer to the true value. And by the late 19th century, Albert Michelson had developed extraordinarily precise techniques using interferometry, the interference of light, waves. Michelson devoted much of his career to measuring the speed of light with ever-increasing precision, eventually determining it to within a fraction of a kilometer per second. Today, we know the speed of light so precisely that we actually define the meter in terms of it. 1 meter is defined as the distance light travels in 1,299,792,458th of a second. We've essentially said that the speed of light is exactly 299,792,458 meters per second by definition. The measurement is no longer about finding light speed. It's about defining our units of distance to match light speed. But here's where things get strange. Really strange. As physicists studied light more carefully in the 19th century, They encountered a puzzle that would eventually shatter our understanding of space and time. A puzzle that seemed like a minor technical issue but turned out to reveal something fundamental about the nature of reality. By the mid-1800s, scientists understood that light was a wave. James Clerk Maxwell, the Scottish physicist, had unified electricity and magnetism into a single theory, one of the great intellectual achievements in the history of science. Maxwell showed that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. This mutual creation allows electromagnetic disturbances to propagate through space as waves. When Maxwell calculated the speed at which these electromagnetic waves should travel, using only the known properties of electricity and magnetism, he got a number that matched the measured speed of light almost exactly. This couldn't be a coincidence. Light was electromagnetic radiation. The light you see, the radio waves that carry signals, the X-rays that show your bones, the microwaves that heat your food, all are electromagnetic, waves differing only in their wavelength and frequency. This was a triumph of theoretical physics. Maxwell had explained what light actually is, but the explanation raised a troubling question. Waves need a medium to travel through. Water waves travel through water. Sound waves travel through air. When you speak, your vocal cords create pressure variations in the air, and these variations propagate outward as sound waves. Without air, there's no sound. Astronauts on the moon can't hear each other speak except through radio. The moon has no atmosphere, no medium for sound to travel through. So what did light waves travel through? Space seems empty. There's no air between the Earth and the Sun, yet light crosses that void easily. Scientists propose that space was filled with an invisible substance called the luminiferous ether. This ether was supposedly everywhere, perfectly transparent, completely weightless, and yet somehow rigid enough to support the incredibly fast vibrations of light waves. It was a strange substance, but it seemed necessary. Without a medium, how could light waves exist? If the ether existed, then Earth must be moving through it as it orbits the Sun at about 30 kilometers per second. And this should have a detectable effect. When you're on a moving boat, the water seems to flow past you even if the water itself is still. Similarly, Earth's motion through the ether should create an ether wind that affects the apparent speed of light. Think about it this way. If you're standing still and throw a ball, it moves at whatever speed you throw it. But if you're walking forward and throw the ball in the direction you're walking, the ball moves faster relative to the ground. If you throw it backward, it moves slower. The ball's speed relative to the ground depends on your speed. Light should work the same way if it's traveling through an ether medium. When Earth moves toward a light source, the light should reach us faster, like running toward an oncoming ball. When Earth moves away, the light should take longer to reach us. The ether wind should cause measurable variations in the speed of light, depending on direction. In 1887, Albert Michelson and Edward Morley conducted what became one of the most famous experiments in the history of science. They built an incredibly sensitive interferometer designed to detect the ether wind. The device was a marvel of precision engineering. Mounted on a massive stone slab floating in a pool of mercury to isolate it from the vibrations. The interferometer split a beam of light in two, sending the beams in perpendicular directions, bouncing them off mirrors, and then recombining them. When light waves recombine, they interfere with each other. If the waves are in phase, their peaks and troughs align, and they add together constructively. If they're out of phase, peaks meet troughs, and they cancel out destructively. The pattern of light and dark bands created by this interference is extremely sensitive to any difference in the travel time of the two beams. If Earth was moving through the ether, light traveling in the direction of Earth's motion should be slightly affected differently than light traveling perpendicular to that motion. The mathematics predicted a detectable difference in the time the two beams took to complete their journeys. This difference would show up as a shift in the interference pattern when the beams recombined. Michelson and Morley's apparatus was sensitive enough to detect a shift much smaller than what the theory predicted. They performed the experiment multiple times, at different times of day, at different times of year when Earth was moving in different directions through space. They rotated the entire apparatus to test different orientations. They found nothing. No shift, no ether wind. The speed of light was exactly the same in every direction, regardless of Earth's motion through space. This was baffling. The experiment was well designed. The equipment was precise. The physics seemed clear. Yet the predicted effect simply wasn't there. Scientists tried to explain it away. Maybe the ether was dragged along by Earth's motion, like air inside a moving car. Maybe the apparatus was contracting in the direction of motion in a way that exactly compensated for the expected effect. But every attempt to salvage the ether theory created new problems, required new assumptions, made the theory more complicated and less convincing. For nearly 20 years, the null result of the Michelson-Morley experiment hung over physics like a dark cloud. Something was wrong with our understanding of light, of motion, of space itself, but no one could figure out what. Then, in 1905, a 26-year-old patent clerk in Switzerland named Albert Einstein published a paper that changed everything. Einstein wasn't working at a university. He wasn't part of the physics establishment. He examined patent applications during the day and did physics in his spare time. But he had a gift for seeing to the heart of problems, for questioning assumptions that others took for granted. Einstein took a radically different approach to the puzzle. Instead of trying to explain why the Michelson-Morley experiment didn't show what it should have shown, he asked a different question. What if the experiment showed exactly what it should have shown? What if the speed of light really is constant regardless of your motion? This seems impossible at first. It violates everything we know about how speeds work. If you're on a train moving at 100 kilometers per hour, and you throw a ball forward at 20 kilometers per hour, someone standing on the platform would see the ball moving at 120 kilometers per hour. Speeds add together. This is basic physics, basic common sense that everyone learns as a child. If I'm moving and I throw something in my direction of motion, it moves faster relative to the ground. But Einstein said that light doesn't work this way. If you're on a spaceship, traveling at half the speed of light, and you shine a flashlight forward, you don't see the light moving away from you at half the speed of light. You see it moving at the full speed of light. 299,792 kilometers per second, exactly. Just as if you were standing still. And here's the truly mind-bending part. Someone watching you from outside, stationary relative to you, also sees your flashlight beam moving at the speed of light. Not 1.5 times the speed of light, as you might expect if speeds added normally. They see exactly the same speed you do. 299,792 kilometers per second. Both observers measure the same speed for the light beam, even though they're moving relative to each other at half the speed of light. How is this possible? It seems like a contradiction. Speeds should add. If you're moving, At 50% of light speed, and the light is moving at 100% of light speed relative to you, shouldn't the light be moving at 150% of light speed relative to a stationary observer? No, it doesn't work that way. And this isn't a subtle measurement effect or an optical illusion. It's a fundamental fact about how the universe operates. Einstein realized that the only way this could work is if our assumptions about space and time are wrong. We think of space as a fixed stage where events happen, an absolute backdrop against which objects move. We think of time as a universal clock that ticks at the same rate for everyone, everywhere, regardless of their motion or location. Newton had codified these assumptions into his physics 2 centuries earlier, and they seemed obviously true. But if the speed of light is truly constant for all observers, then space and time themselves must be flexible. They must adjust to ensure that everyone measures the same speed for light. The stage isn't fixed. The clock doesn't tick uniformly. Space and time bend and stretch and warp to accommodate the constancy of light speed. This led Einstein to his theory of special relativity, and it revealed something stunning. The speed of light isn't special because of light. It's special because it's built into the structure of space-time itself. What we call the speed of light is actually the speed at which causality propagates through the universe. It's the maximum speed at which information, influence, or any kind of cause and effect relationship can travel. Light happens to travel at this speed because photons have no mass and therefore naturally travel at the universe's fundamental speed limit. But the limit would exist even if light didn't. It's not about light, it's about the geometry of reality. To understand why this matters, think about what speed really means. Speed is distance divided by time. You travel a certain distance in a certain amount of time. Simple enough, but Einstein showed that distance and time are not independent quantities that can be measured separately. They're two aspects of a single thing called space-time, and the relationship between them is governed by this fundamental constant that we happen to call the speed of light. When you move through space, something strange happens to your relationship with time. The faster you move through space, the slower you move through time. Not because of some illusion or measurement error, but actually physically, genuinely. Time itself passes more slowly for you when you're moving fast relative to someone else. This isn't science fiction. It's been measured countless times with extraordinary precision. Atomic clocks flown on airplanes tick slightly slower than identical clocks on the ground. The difference is tiny, a few nanoseconds for a long flight, but it's real and measurable. Particles created in accelerators live longer when they're moving fast than when they're at rest. Muons, subatomic particles created when cosmic rays hit the upper atmosphere, should decay before reaching the ground. But we detect them at sea level because time dilation extends their lifetimes from their perspective. GPS satellites have to correct for relativistic time dilation because they're moving fast enough relative to the ground that the effect is measurable and significant. Without these corrections, GPS would drift by kilometers per day. But what does any of this have to do with the speed limit? Here's the connection that reveals the deep structure of reality. As you move faster and faster through space, time slows down more and more. At half the speed of light, time passes about 15% slower. At 90% of light speed, time passes about 2.3 times slower. At 99% of light speed, time passes about 7 times slower. And as you approach the speed of light, something mathematical happens. time approaches a standstill. The closer you get to light speed, the more time slows down. At exactly the speed of light, time would stop completely. This has profound implications. If you could somehow reach the speed of light, you would experience no time at all. Your journey, no matter how far, would be instantaneous from your perspective. You could cross the entire universe, a journey of billions of light years, and experience zero elapsed time. But from the perspective of anyone watching you, you'd be frozen in time, taking forever to complete your journey. And this reveals the real nature of the speed limit. It's not that you can't go faster than light because something would stop you, because you'd hit a wall or run out of fuel or violate some rule. It's that the question of going faster than light doesn't even make sense in the geometry of space-time. Speed is distance divided by time, but at light speed, time stops. You can't divide by zero. Beyond light speed, time would have to go backward. And this isn't just weird. It's logically impossible in ways we'll explore deeply. The very concept of going faster than light becomes incoherent when you understand what speed, distance, and time actually are. The speed of light is not a speed limit in the way a posted highway limit is a speed limit. It's not a rule that could in principle be broken if you had enough power or clever enough technology. It's a fundamental feature of how space and time are woven together into space-time. Asking why nothing can go faster than light is like asking why north can't go more north, or why you can't draw a four-sided triangle. The question assumes something that doesn't fit with reality. But perhaps you're thinking, this all sounds very abstract. Why should we care about the geometry of space-time? What does this have to do with Feynman, and with understanding why reality works the way it does? That's what we'll explore in the sections ahead, because Feynman saw something about this that goes beyond just the physics. He saw why this speed limit isn't a limitation but a requirement. Without it, cause couldn't lead to effect. Without it, the universe as we know it couldn't exist. To understand what Feynman uncovered, we need to go deeper into the relationship between space and time. We need to understand what physicists call causality, the principle that causes must precede their effects, that the future flows from the past in an ordered way, and we need to understand what would happen if this principle could be violated, because here's the stunning truth that will reshape how you see everything. The speed of light isn't just a quirk of physics, an interesting fact about electromagnetic radiation. It's what makes the universe possible. It's what allows events to have consequences. It's what allows decisions to matter. It's what allows reality to be coherent at all. Richard Feynman spent his career exploring the deepest structure of reality. He won the Nobel Prize for his work on quantum electrodynamics, the theory that describes how light and matter interact at the most fundamental level. And in his explorations, he came to see that the speed of light sits at the very heart of physics, not as an arbitrary constant that happened to have a certain value, but as a necessary feature of any universe that can contain cause and effect, action and consequence, past and future. Let's pause and appreciate what we've learned so far. Light has a finite speed. This was discovered centuries ago by Romer watching Jupiter's moons. That speed is constant regardless of your motion. This was demonstrated by the Michelson-Morley experiment and explained by Einstein. This constancy requires space and time to be flexible, interconnected, woven into a unified space-time where motion affects the passage of time. This was understood in the early 20th century and confirmed by countless experiments since. But the deepest insight, the one that reveals what this all really means, came later. It came from understanding that this speed isn't about light at all. It's about information. It's about causality. It's about the fundamental structure that allows effects to follow from causes. And this is what Feynman saw so clearly with the visual intuition and physical insight that made him unique among physicists. Not just that the speed of light is constant, but why it must be constant for reality to work at all. Why violating this limit wouldn't just be difficult or energy prohibitive, but would break the logical structure of the universe itself. The speed of light guards the order of cause and effect. It ensures that the past comes before the future. It makes science possible, makes decisions meaningful, makes existence coherent. Without it, without this limit woven into the fabric of space-time, reality would dissolve into paradox and contradiction. That's what we're going to understand. That's what Feynman uncovered. And once you see it, nothing looks the same. Richard Feynman was not like other physicists. He had an almost supernatural ability to see through mathematical complexity to the physical reality underneath. While other physicists manipulated equations, pushing symbols around on paper according to formal rules, Feynman thought in pictures. He visualized what was actually happening. He would close his eyes and imagine particles bouncing off each other, fields rippling through space, forces reaching out and pulling. And this visual, intuitive approach led him to insights that transformed physics in ways that are still being understood today. Feynman was born in 1918 in Far Rockaway, Queens, New York. From childhood, he was fascinated by how things worked. His father, a uniformed salesman, taught him to question everything, to never accept authority as a substitute for understanding. When young Richard asked why a ball in a wagon rolled to the back when the wagon was pulled forward, his father didn't just say inertia, he explained that nobody really knows why. The ball tends to stay still, and it's the wagon that moves forward underneath it. The ball doesn't know the wagon moved. This way of thinking, questioning the obvious, digging beneath surface explanations, became Feynman's signature approach. As a teenager, Feynman fixed radios in his neighborhood, figuring out problems that stumped adult repairmen. He taught himself trigonometry, advanced algebra, and calculus from library books. He invented his own mathematical notation because he found the standard symbols unclear. He wasn't content to know that something was true. He needed to understand why it was true, what it really meant, how it connected to everything else. After completing his undergraduate degree at MIT and his doctorate at Princeton, Feynman worked on the Manhattan Project during World War II. He was one of the youngest physicists at Los Alamos, known for his brilliance and his irreverence. He would crack safes for fun, play bongo, drums, and challenge senior scientists with uncomfortable questions. Even among the extraordinary collection of minds assembled to build the atomic bomb, Feynman stood out. But his most important work came afterward, when he tackled one of the deepest problems in theoretical physics, the problem of quantum electrodynamics, or QED. Quantum electrodynamics is the theory that combines quantum mechanics with special relativity to describe how light and matter interact at the most fundamental level. When an electron absorbs a photon, when light bounces off a mirror, when atoms emit the light we see, QED describes what's happening. It's the theory of the electromagnetic force at the quantum scale. The basic framework of QED had existed since the late 1920s and early 1930s. Paul Dirac had written down the fundamental equations. But there was a terrible problem. When physicists tried to calculate anything beyond the simplest processes, they got nonsensical answers. Infinities kept appearing. The mass of the electron came out as infinite. The charge of the electron came out as infinite. Every calculation beyond the first approximation blew up into meaningless infinities. This wasn't just a mathematical inconvenience, it threatened to make the entire theory useless. A theory that predicts infinite answers is no theory at all. It's just symbols on paper. For nearly 2 decades, QED remained stuck, its promise unfulfilled, its calculations blocked by these stubborn infinities. Feynman, along with 2 other physicists working independently, Julian Schwinger at Harvard and Shinichiro Tomonaga in Japan, found ways to tame these infinities and make the theory work. Their approach, called renormalization, was subtle and powerful. The infinities were still there, lurking in the equations, but Feynman showed that they could be absorbed into the definitions of the electron's mass and charge, leaving finite, calculable predictions for everything else. This might sound like a mathematical trick, sweeping infinities under the rug, but it worked. Renormalized QED made predictions that could be tested. And when physicists compared these predictions to experiments, the agreement was extraordinary. QED predicted the magnetic moment of the electron to more than 10 decimal places. Experiments confirmed the prediction to all those decimal places. It was and remains the most precisely verified theory in all of science. For this work, Feynman, Schwinger, and Tomonaga shared the Nobel Prize in Physics in 1965. But the significance of their achievement went far beyond the prize. They had shown that quantum mechanics and special relativity could be combined consistently. They had created a framework that would later be extended to describe all the fundamental forces except gravity. They had opened the door to the standard model of particle physics, the crowning achievement of 20th century physics. But what made Feynman's approach truly special, what set it apart from Schwinger's more formal mathematical methods, was his diagrams. Feynman diagrams are a way of visualizing particle interactions. Instead of pages of complicated equations with Greek letters and integrals and summations, you draw simple pictures. Particles are represented as lines moving through space-time. Interactions are represented as vertices where lines meet. The propagation of forces is represented as wiggly or dashed lines connecting vertices. An electron absorbing a photon. Draw a straight line for the electron, a wavy line for the photon, and have them meet at a point. The electron scattering off another electron by exchanging a photon. Draw 2 electron lines coming in, a photon line connecting them, and 2 electron lines going out. 2 photons creating an electron-positron pair. Draw 2 wavy lines coming in, meeting at a point, and a loop where an electron and its antiparticle briefly exist before annihilating. These diagrams aren't just pretty pictures or pedagogical tools. Each diagram corresponds to a precise mathematical expression. The rules for translating diagrams into equations are exact. By drawing all the possible diagrams for a particular process and adding up their mathematical contributions, you can calculate the probability of that process occurring. The diagrams make visible what the equations describe. They show what's physically happening. An electron emits a photon, recoils, later absorbs another photon, changes direction. All of this is visible in the diagram. The structure of the interaction is laid out spatially, with time typically running upward on the page and space running horizontally. When Feynman first presented his diagrams at a physics conference in 1948, Many senior physicists were skeptical. The diagrams seemed too simple, too intuitive, almost childlike compared to the rigorous formal methods that Schwinger was developing. How could drawing pictures be legitimate physics? But Feynman showed that his diagrams gave the same answers as Schwinger's pages of equations, and they gave the answers faster, more intuitively, with less chance of error. Over time, Feynman diagrams became the standard language of particle physics. Today, any particle physicist can read and draw these diagrams fluently. They're how the field thinks about fundamental processes, and at the heart of these diagrams, built into their very structure, is the speed of light. Not as an afterthought or an added constraint that must be checked, but as a fundamental feature of how particles can interact, how causes can produce effects, how reality unfolds through time. To understand what Feynman saw encoded in his diagrams, we need to grasp something called the space-time interval. This is one of the most important concepts in all of physics, and once you understand it, the speed of light reveals its true significance. In ordinary space, we measure distances using the Pythagorean theorem. If you move 3 meters east and 4 meters north, you've traveled 5 meters in a straight line. Why? Because 3 squared plus 4 squared equals 9 plus 16 equals 25, and the square root of 25 is 5. The Pythagorean theorem tells us how to combine perpendicular distances into a total distance. In space-time, something similar but crucially different happens. Events are separated not just by space, but also by time. You might be here now and there later. The separation between these two events has both a spatial part, how far away you've moved, and a temporal part, how much time has passed. When we calculate the space-time interval between two events, something strange appears. We don't just add the space part and the time part the way the Pythagorean theorem adds perpendicular distances. We subtract them. The space-time interval squared equals the time difference squared, times the speed of light squared, minus the space distance squared. Time and space contribute with opposite signs. One has a plus, the other has a minus. This seemingly small mathematical detail changes everything. Why does the speed of light appear in this formula? Because time and space are measured in different units. Time is measured in seconds, space in meters. To combine them, you need a conversion factor that turns time into a distance, or distance into a time. The speed of light is that conversion factor. 1 second of time corresponds to about 300,000 kilometers of distance. The distance light travels in that second. But the opposite signs are what really matter. This might seem like a technical detail of no practical importance, but it has profound consequences. It means that there are 3 fundamentally different types of relationships between events in space-time. First, there are events separated by more time than space. If you multiply the time between them by the speed of light, you get a bigger number than the spatial distance between them. What does this mean physically? It means light would have had enough time to travel from one event to the other. A signal could have passed between them. A cause at one event could have produced an effect at the other. These are called time-like separated events, and they can have a cause and effect relationship. One event can genuinely influence the other. Second, there are events separated by more space than time. Light wouldn't have had time to travel between them. Even moving at 300,000 kilometers per second, light couldn't get from one event to the other. These are called space-like separated events, and they cannot have a direct cause and effect relationship. Nothing traveling at or below light speed could connect them. They're too far apart and too close in time. Third, there are events separated by exactly the amount of space that light could traverse in the time between them. These are called light-like or null-separated events. Light itself, or anything else massless traveling at light speed, could just barely travel between them. These events sit exactly on the boundary between what can and cannot be causally connected. This division of space-time into regions that can and cannot influence each other is called the light cone. And this is where things get really interesting. Imagine yourself at a particular point in space-time. You're at a particular place at a particular moment. Now draw lines extending forward in time, representing all the paths light could take from your current position. These aren't just lines going straight up. Light could go left or right, forward or backward, in any direction. So the lines form a cone shape, expanding outward as time moves forward, like a three-dimensional cone extending into the future. Everything inside this cone is your future light cone. These are all the events you could possibly influence. No matter what you do, no matter how fast you travel, as long as you can't exceed light speed, you can only reach events inside your future light cone. Events outside the cone are forever beyond your influence. You can't get there in time. No message you send, no action you take can affect them. Similarly, draw lines extending backward in time. This is your past light cone. These are all the events that could possibly have influenced you. Everything that contributed to your current state, every cause that affected who you are right now, must lie in your past light cone. If an event is outside your past light cone, it couldn't have affected you. The light from it, the information from it, hasn't had time to reach you yet. Outside these cones, both past and future, is what physicists call the elsewhere. Events in the elsewhere cannot influence you, and cannot be influenced by you. They're causally disconnected from you. They're not your past or your future from any physical standpoint. They're simply elsewhere. They exist, they happen, but they have no causal relationship to your present moment whatsoever. This light cone structure isn't just a mathematical abstraction. It's physically real. It divides the universe into what can affect what. It determines the boundaries of cause and effect. And it's built into the structure of space-time itself, emerging automatically from the opposite signs in the space-time interval formula. Feynman's diagrams are built on this light cone structure. When you draw a Feynman diagram, particles move along paths through space-time, but these paths aren't arbitrary. They respect the light cone. Massive particles, things with weight like electrons and protons, move along paths that stay inside the light cone. They move slower than light along what are called time-like paths. Photons, particles of light with no mass, move along paths right on the surface of the light cone. They move at exactly light speed along what are called null or light-like paths. Information, influence, cause and effect, these all flow from inside the past light cone to inside the future light cone. A particle can affect another particle only if their interaction respects this structure. An electron can emit a photon, and that photon can be absorbed by another electron, but only if the geometry works out. Only if the photon's path along the light cone connects the two events properly. What happens at the boundary? What happens if something tried to move faster than light? This is where Feynman's insight becomes truly profound. This is where the speed limit reveals its true nature. In Feynman's picture, particles moving faster than light would have to travel along paths outside the light cone. Their paths would be space-like rather than time-like. They'd be cutting across the elsewhere, connecting events that have no business being causally connected. And here's where things get genuinely bizarre. Remember how time and space have opposite signs in the space-time interval? This means that for a space-like path, traveling along it would be mathematically equivalent to moving backward in time from some reference frames. Let me explain this more carefully because it's crucial to understanding why the speed limit exists. In special relativity, there's no absolute notion of simultaneous. Events that happen at the same time, according to one observer, might happen at different times, according to another observer, moving relative to the first. If you're standing on a train platform and see two lightning strikes at different ends of the platform at the same moment, someone on a moving train might see one strike before the other. This is called the relativity of simultaneity, and it's a direct consequence of the constant speed of light. This sounds strange, but it's been verified experimentally countless times. It's real. Simultaneity is relative. For events that are time-like separated, events where one could have caused the other, all observers agree on which event happens first. The ordering of cause and effect is preserved. You might disagree about how much time passed between them, but you all agree on the order. Everyone agrees that the cause came before the effect. But for events that are space-like separated, events outside each other's light cones, different observers can disagree about which happened first. To some observers, event A happened before event B. To others moving differently, event B happened before event A. The order isn't fixed. This is fine for space-like separated events in a normal universe because they can't have a causal relationship anyway. Nothing can travel between them. So it doesn't matter if observers disagree about which happened first. There's no cause and effect to preserve. They're just two unconnected events, and different people can disagree about their order the way you might disagree about which painting in a gallery is more to the left. But now, imagine a hypothetical faster-than-light particle, what physicists call a tachyon. This particle would travel along space-like paths. It could go from event A to event B, where these events are space-like separated. It would connect events that shouldn't be connected. And here's the catastrophe. To some observers, the tachyon would appear to travel from A to B. They see it leave A and arrive at B. But to other observers, moving at a different velocity relative to the tachyon's path, the tachyon would appear to travel from B to A. They see it leave B and arrive at A. The direction of travel would reverse depending on who's watching. This isn't a matter of perception or optical illusion. It's a fundamental consequence of how space-like paths work in space-time, with relativity of simultaneity. Different reference frames see different orderings, and for a tachyon path, that means they see different directions of travel. Even worse, some observers would see the tachyon arrive before it departed. The effect would precede the cause. The particle would reach its destination before it left its origin. From their perspective, time would run backward for this particle. This isn't just strange. It leads to logical contradictions that would make reality incoherent. This creates a catastrophic problem. If something could travel along space-like paths, connecting events outside each other's light cones, it would appear to travel backward in time from certain reference frames. Information from the future could reach the past. And this doesn't just create strange situations. It creates logical contradictions, paradoxes where effects prevent their own causes. We'll explore these paradoxes in detail shortly, but the conclusion is clear. Such contradictions cannot exist in a coherent universe. The speed limit isn't optional. It's what keeps reality logically consistent. Feynman understood this at a deep level. He saw it in the mathematics of his diagrams. He saw it in the structure of quantum electrodynamics. In his work on QED, Feynman developed the path integral formulation of quantum mechanics. This is one of the most profound reconceptualizations of quantum physics ever achieved. In the standard picture of quantum mechanics, developed by Schrödinger and Heisenberg in the 1920s, particles are described by wave functions that evolve according to certain equations. In Feynman's path integral picture, something different and stranger happens. In Feynman's formulation, a particle going from point A to point B doesn't follow a single path through space-time. Instead, it follows all possible paths simultaneously. Every conceivable trajectory from A to B contributes to the final result. The straight path contributes. The curved paths contribute. The wild, looping paths contribute. Even paths that seem to briefly travel backward in time contribute. The probability of the particle actually getting from A to B is calculated by summing over all these paths, adding up their contributions with appropriate mathematical weights. The paths interfere with each other, some adding constructively, some cancelling out. The final answer emerges from this sum over all possibilities. This sounds like the perfect setup for faster-than-light paths to contribute. If all paths are included, surely some of them go faster than light. But here's the remarkable thing. When you do the mathematics correctly, the contributions from faster-than-light paths cancel out or are exponentially suppressed. What remains, what actually contributes to physical predictions, are the paths that respect causality. Feynman didn't put this in by hand. He didn't add a rule saying, exclude paths that violate causality. It emerges from the mathematics. The structure of quantum field theory, when properly combined with special relativity, automatically enforces the speed limit. The light cone structure is preserved because the mathematics requires it. When Feynman looked at his diagrams, he saw this light cone structure underlying everything. Every interaction between particles respects the light cone. Every exchange of force carriers happens in a way that preserves causality. Every physical process flows from past to future, from cause to effect, in a way that all observers can agree on. The speed of light isn't an imposed constraint that some clever engineer might one day circumvent. It emerges from the mathematical structure of how particles can possibly interact in a consistent quantum theory. It's not a rule of physics. It's a feature of logic and mathematics when applied to space-time. This was Feynman's great insight. The speed limit isn't about engineering difficulties or energy requirements or technological limitations. It's about logic. It's about the structure of reality. A universe without this speed limit wouldn't just be strange or difficult to navigate. It would be contradictory, incoherent, logically impossible. Think about what causality means for your own life. Every decision you make has consequences that flow forward in time. Your past shapes your present, and your present shapes your future. You can remember yesterday, but not tomorrow. You can plan for next year, but not change last year. You can learn from your mistakes because your mistakes precede the learning. This seems so basic, so obvious, so much a part of everyday experience that we rarely think about it. Of course, the future flows from the past. Of course, causes precede effects. Of course, you can't remember what hasn't happened yet. These seem like trivial observations, almost too obvious to mention. But Feynman saw that this basic structure of reality, this ordinary everyday flow from past to future, depends on the speed limit. Without the limit, without the light cone, without the division of space-time into regions that can and cannot influence each other, causality would break down. Past and future would become confused. Causes and effects would lose their meaning. The very concepts that structure our experience of time and change would become incoherent. The speed of light, that precise value of 299,792.458 kilometers per second, isn't arbitrary. It's not a number that could have been different in some other universe. It's the relationship between space and time that makes causality possible. It's the conversion factor between spatial distance and temporal duration. It's the exchange rate that lets space and time function as aspects of a single, unified space-time, while maintaining the crucial distinction between what can affect what. Feynman had a gift for explaining complex ideas simply. He once said that if you can't explain something to a freshman, you don't really understand it. He wasn't satisfied with mathematical formalisms that got the right answers. He needed to understand what the mathematics meant physically. And when Feynman explained special relativity, he cut through the mathematics to the physical meaning with a beautiful picture that makes everything clear. Here's how Feynman thought about it. Everyone is moving through space-time at the same total rate. The rate is the speed of light. You can't move through space-time faster or slower than the speed of light. You're always traveling at exactly c through the four-dimensional fabric of space-time. But here's the key. Your motion can be divided between space and time. If you're standing still in space, all your motion through space-time is in the time direction. You're not moving through space at all. So all your space-time velocity goes into moving through time. Time passes for you at its maximum rate. As you start moving through space, walking, then running, then driving, then flying, some of your motion through space-time shifts from the time direction to the space direction. But your total motion through space-time stays the same. It's always c. So if more goes into space, less remains for time. Time passes more slowly for you. The faster you move through space, the more of your space-time motion is diverted from time, and the slower time passes. At 90% of light speed, a significant fraction of your space-time motion is going into the spatial direction. Time runs noticeably slower. At 99% of light speed, almost all your space-time motion is spatial. Time barely passes at all. At exactly the speed of light, all your motion through space-time would be in the spatial direction. None would be left for time. Time would stop completely. This is why light itself, which travels at c through space, experiences no time. A photon travels from a distant star to your eye, a journey that might take millions of years from your perspective. But from the photon's perspective, if a photon could have a perspective, no time passes at all. The photon leaves the star and arrives at your eye in the same instant of its own experience. This picture shows why you can't exceed light speed. You can't have more motion in the space direction than your total motion through space-time. You're always moving at c through space-time. That's fixed. You can redirect that motion, putting more into space and less into time. But you can't exceed the total. You can't divert more than 100%. The speed of light isn't a barrier you approach and can't quite reach because something stops you. It's a mathematical boundary that defines the relationship between space and time. Asking to exceed it is like asking to be more than completely turned around. If you're facing north, you can turn, but you can't be facing more north than north. Feynman also emphasized that special relativity isn't just a theory about moving objects or high-speed travel. It's a theory about space and time themselves. The speed of light appears everywhere in fundamental physics. It appears in the equations of electromagnetism. It appears in the structure of space-time. It appears in how energy and mass are related. Einstein's famous equation E equals mc squared, where c is the speed of light. This constant isn't something light happens to travel at, like how fast a particular car happens to go. It's built into the fundamental fabric of reality. It would be there even if light didn't exist. It's the speed of causality, the speed at which cause can produce effect, the speed at which the universe unfolds. What Feynman uncovered, through his diagrams and his intuitive physical pictures, was something profound about the geometry of existence. The light cone isn't just a mathematical abstraction. It's the structure that separates what can influence what. It's the architecture of cause and effect. And the speed of light is what defines the architecture, converting between space and time, setting the boundaries of causal connection. Feynman saw this geometry underlying every particle interaction, every quantum process, every physical phenomenon. The speed limit wasn't imposed on physics. It was physics, at the deepest level. And if paradoxes become possible, if causes can be their own effects, if time can loop back on itself, then logic fails. Consistency becomes impossible. Predictions become meaningless. The whole edifice of physics, of science, of rational understanding collapses. This is what Feynman saw. The speed of light isn't a limitation. It's a requirement. It's what makes reality possible. It's what allows the universe to be a place where things happen in an orderly way, where causes lead to effects, where the future flows from the past, where science can work and understanding can be achieved. The light cone structure that emerges from the speed of light is the scaffolding of causality. It's what separates past from future, what defines what can affect what makes the universe coherent. Without it, there would be no arrow of time. Without it, there would be no distinction between what has happened and what will happen. Without it, reality would be a jumbled mess of paradoxes and contradictions. And Feynman saw all of this, not through philosophical argument, but through the hard mathematics of quantum field theory. He saw the speed limit emerge from the equations, protect causality in every interaction, preserve the light cone structure even in the strange probabilistic world of quantum mechanics. That's what Feynman uncovered. The speed of light is the guardian of cause and effect. It's what makes the universe make sense. Let's go deeper into causality and really understand what's at stake. Because causality isn't just a philosophical concept that academics debate in seminar rooms. It's the basis of everything we know about how the universe works. It's the foundation of science, of prediction, of understanding itself. And Feynman's work revealed just how intimately connected causality is to the speed of light. The two are bound together so tightly that you cannot have one without the other. What is causality exactly? At its simplest, causality means that effects follow from causes. If you throw a ball, the ball moves because you threw it. The throwing caused the motion. The motion didn't cause the throwing. There's an order, a direction, a flow from cause to effect that cannot be reversed. When you strike a match, it ignites. The striking causes the ignition. When you release an object, it falls. The release causes the fall. When you speak words, sound waves propagate outward. The speaking causes the sound. In every case, there's a clear temporal order. First the cause, then the effect. First the action, then the consequence. This seems obvious, almost trivially true, so obvious that it hardly seems worth stating. Of course, causes come before effects. Of course, actions precede their consequences. This is just how the world works. But consider what this really means. It means that the universe has a temporal structure, a distinction between past and future that's more than just arbitrary labeling. The past is fixed, determined, already happened. It's done. You can't change it. The future is open, undetermined, not yet happened. It's still being shaped. Causes live in the past, effects live in the future. Information flows from past to future, not the reverse. This asymmetry between past and future is so fundamental to our experience that we rarely question it. You remember yesterday, but not tomorrow. You can plan for next week, but not change last week. You can learn from past mistakes, but not from future ones. The past is a closed book. The future is a blank page being written. Without this structure, science would be impossible. When we do experiments, we set up initial conditions and observe what happens. We manipulate causes and measure effects. We change something here and see what changes there. The whole scientific method assumes this causal arrow pointing from past to future. If effects could precede causes, if the future could influence the past, experiments would be meaningless. The outcome of an experiment might determine its initial conditions rather than the other way around. Changing something today could change what happened yesterday. Nothing would be reproducible because the past itself would be changeable, determined partly by a future that hasn't happened yet. Even everyday life depends utterly on causality. You make decisions based on expected consequences. If I do this, then that will happen. If I study, I'll learn. If I practice, I'll improve. If I save money, I'll have resources later. All of this reasoning assumes that your actions today shape your future, not your past. You plan for the future based on past experience. You've learned that certain causes lead to certain effects. Fire is hot, ice is cold, dropped objects fall. These regularities, learned from past observation, guide your expectations about the future. But this only works if the future is like the past. If the same causes produce the same effects. If the causal structure of the universe is consistent. You learn from mistakes, adjusting future behavior based on past outcomes. You touched a hot stove once and it hurt. You don't touch hot stoves anymore. But this learning only makes sense if the past mistake caused the present knowledge, which can influence future behavior. If causality could run backward, your future behavior might determine your past mistake, which would determine your present knowledge, and the whole chain becomes an incomprehensible tangle. Now, here's the crucial connection that Feynman understood so deeply. Causality is protected by the speed of light. The light cone structure of space-time keeps causes and effects properly ordered. For any two events that could possibly have a causal relationship, where one could have influenced the other, all observers in all reference frames agree on which event happens first. The speed limit ensures this universal agreement. This is remarkable when you think about it. Special relativity tells us that observers moving relative to each other will disagree about all sorts of things. They'll disagree about distances. A meter stick looks shorter to someone moving past it. They'll disagree about time intervals. A clock ticks slower when it's moving. They'll even disagree about which events are simultaneous. Two events that happen at the same time for you might happen at different times for someone moving relative to you. With all this disagreement about space and time, you might expect complete chaos. how can anyone agree on anything? But there's one thing all observers agree on. If event A could have caused event B, if A is in B's past light cone, then everyone agrees that A happened before B. The ordering of cause and effect is preserved. This isn't a coincidence. It's not something physicists added as an extra assumption. It emerges automatically from the mathematics of space-time with a speed limit. The light cone structure, that division of space-time into regions that can and cannot influence each other, is what saves causality from the relativity of simultaneity. Let's explore what happens when we imagine violating this limit. Let's really dig into the thought experiments and see exactly how things fall apart, because understanding this in detail reveals just how fundamental the speed limit truly is. Suppose, hypothetically, that you could send a message faster than light. Not just a little faster, but much faster. Let's say essentially instantaneously across any distance. Science fiction is full of such devices. Ansible communicators, subspace radio, hyperwave transmitters, whatever you want to call them. Devices that let you talk to someone light years away as easily as making a phone call. What would actually happen if such a device existed? First, let's set up a thought experiment carefully. You're at point A on Earth. Your friend is at point B, 1 light year away, on a space station orbiting a distant star. You have matching instantaneous communicators. You send a message to your friend. Because the message is instantaneous, from your perspective, your friend receives it at the exact moment you send it. No delay at all. Your friend reads your message, composes a reply, and sends it back with their own instantaneous communicator. From your friend's perspective, you receive the reply at the exact moment they sent it. Again, no delay. So far, this might seem fine, even convenient. You send a message, your friend receives it instantly. They reply instantly, and you receive the reply instantly. A conversation that would take 2 years at light speed, 1 year for your message to get there, and 1 year for the reply to get back, happens in no time at all. Wouldn't that be wonderful? But here's where special relativity enters and ruins everything. There's a third person in this scenario. Let's call her Carol. Carol is traveling at high speed through space, moving from B toward A. She's not at A or B. She's somewhere in between, moving at a significant fraction of the speed of light. Because of the relativity of simultaneity, events that are simultaneous for you are not simultaneous for Carol. This isn't just a matter of perception or communication delay. It's a fundamental feature of how space and time work. Different reference frames slice space-time differently, and what counts as the same moment depends on how you're moving. From your perspective, you sent your message and your friend received it at the same instant. These events were simultaneous for you. But from Carol's perspective, because she is moving relative to both you and your friend, these events are not simultaneous because of how the mathematics of relativity works out. From Carol's perspective, your friend received the message before you sent it. This sounds impossible. How can your friend receive a message before you send it? But remember, this is what happens with instantaneous communication when combined with the relativity of simultaneity. The message crosses a space-like interval. For space-like separated events, different observers can disagree about the order. And if you're connecting such events with a signal, that signal will appear to travel backward in time from some perspectives. From Carol's perspective, your message didn't just travel faster than light. It traveled backward in time. It arrived before it was sent. And when your friend sends their reply, the same thing happens. From Carol's perspective, The reply also travels backward in time. Now, follow the chain of events from Carol's point of view. Your friend receives a message from you, but wait, you haven't sent it yet according to Carol's clock. Your friend replies. That reply travels backward in time and reaches you, but it reaches you before you sent the original message. You receive a reply to a message you haven't sent yet. The reply contains information about the message you will send. Information from your future has arrived in your present. The instantaneous communicator has become a time machine. And this creates the possibility of paradox. Suppose the message your friend sends back contains information about a decision you're about to make. Maybe the original message you sent, the one you haven't sent yet from Carol's reference frame, asked your friend to confirm whether a coin you're about to flip lands heads or tails. Your friend, having received the message, looked at their screen where the result of your flip was automatically recorded and transmitted, and replied with, "It landed heads." Now you receive this reply. It says heads, but you haven't flipped the coin yet. You're holding the coin in your hand. You were about to flip it, but now you have information from the future about how it will land. This is strange, perhaps even disturbing, but not necessarily paradoxical. Maybe the coin really will land heads. Maybe you can know the future without being able to change it. Some philosophers have proposed such deterministic models, but now suppose you decide to be contrary. You've received a message saying the coin will land heads. You decide you don't want that. You deliberately manipulate the flip so the coin lands tails, or you don't flip at all, or you throw the coin into a fire and destroy it. The message says heads, but the coin landed tails, or didn't land at all. The message was wrong, but the message came from your actual future. It came from what actually happened. How can the message be wrong if it report what actually occurred? You've created a contradiction. The message says X happened, but X didn't happen. You ensured X didn't happen, precisely because the message said it would. The cause of your action was the message, but the message was caused by an event that your action prevented. The causal chain loops back on itself and bites its own tail. This is known as a grandfather paradox, named after the classic example where someone travels back in time and kills their own grandfather before their parent was born, thus preventing their own existence, thus preventing them from traveling back in time, thus allowing their grandfather to survive, thus allowing their existence and around forever. It's also called a bootstrap paradox, or a predestination paradox, or any number of related names for paradoxes involving closed causal loops and self-contradictory histories. They all stem from the same source. If information can travel backward in time, then the future can influence the past. And this creates the possibility of logical contradictions. Not just strange situations or philosophical puzzles, but genuine logical impossibilities where a statement and its negation are both true. Some people have proposed ways around these paradoxes. Clever physicists and science fiction writers have imagined solutions that might rescue faster-than-light communication from logical catastrophe. One proposal is called the Novikov self-consistency principle, named after physicist Igor Novikov. The idea is that the universe somehow prevents paradoxes from occurring. If you could travel back in time or send information to the past, you would only be able to do things that are consistent with what already happened. You couldn't kill your grandfather because something would always stop you. The gun would jam. You'd lose your nerve. You'd discover it wasn't actually your grandfather. Whatever it takes, The universe conspires to maintain consistency. But this just moves the problem. Now you have mysterious constraints on your free will. You think you're free to pull the trigger, but something always prevents you. What force is doing this? How does the universe know what's consistent and what isn't? How does it enforce consistency in real time? These questions have no satisfying answers. And even if you accept such constraints, the Novikov principle still requires a coherent notion of what already happened in a universe where the past can be influenced by the future. If the future can change the past, what does already happened even mean? The concept becomes incoherent. Other physicists have proposed that time travel or backward information flow would split off parallel timelines. You send a message to the past, but instead of changing your own past, you create a new branch of reality. In one branch, events proceed as they originally did. In another branch, events proceed differently because of your message. The timelines don't interact. There are no paradoxes because you're never actually changing anything. You're just creating new versions of reality. This avoids the logical contradictions, but it means there's not really time travel in the sense people usually mean. You're not changing your past. Your grandfather in your timeline stays safely dead or alive, as the case may be. You're just creating a new timeline where a different version of your grandfather meets a different fate. That might be interesting, but it's not the same as actually influencing your own history. Feynman took a more fundamental approach. In his view, these paradoxes aren't puzzles to be solved by clever reasoning or exotic physics. They're symptoms of an impossible assumption. The very assumption that faster-than-light travel or communication is possible leads inevitably to contradictions. And when an assumption leads to contradictions, the assumption must be wrong. This is basic logic. If assuming X leads to a contradiction, then X must be false. Faster-than-light communication leads to the possibility of paradoxes, contradictions, logical impossibilities. Therefore, faster-than-light communication must be impossible. Not just difficult, not just beyond our current technology. Logically impossible given the structure of space-time. This is a subtle but crucial point. The speed limit isn't an engineering problem to be overcome with better technology or more energy. It's a logical necessity given the geometry of space-time. You can't exceed the speed of light for the same reason you can't draw a round square, find a married bachelor, or count to the largest number. It's not that you haven't tried hard enough. The concept itself is incoherent. A round square isn't just a square that's very round or a circle that's somewhat angular. The very definition of square, 4 equal sides and 4 right angles, is incompatible with the definition of round, all points equidistant from a center. The terms contradict each other. No amount of effort can produce a round square because the concept has no coherent meaning. Similarly, faster-than-light travel isn't just very fast travel that happens to exceed a certain speed. Given the structure of space-time, given the relativity of simultaneity, faster-than-light travel is equivalent to backward time travel from some reference frames. And backward time travel leads to logical contradictions. The concept of faster-than-light travel in a universe with our space-time structure is incoherent. Feynman's diagrams made this visible in a beautiful way. In a Feynman diagram, particles are represented by lines moving through space-time. Each line has a direction indicating whether the particle is moving forward or backward in time. Electrons, photons, quarks, all the particles of physics trace paths through the diagrams. One of Feynman's most remarkable insights was that antiparticles, the antimatter partners of regular particles, can be thought of as regular particles moving backward in time. An electron moving forward in time has the same mathematical description as a positron, the electron's antiparticle, moving backward in time. The equations don't distinguish between the two interpretations. This might sound alarming at first. Particles moving backward in time? Isn't that exactly what we said was impossible? If particles can move backward in time, doesn't that allow all the paradoxes and contradictions we just discussed? But here's the key insight. In Feynman's framework, a particle moving backward in time is entirely equivalent to its antiparticle moving forward in time. There are two ways of describing the same mathematical object. There's no actual backward time travel involved. It's like describing a video playing in reverse. You can describe it as time running backward, or you can describe it as an anti-version of the video playing forward. Same thing. Different descriptions. This mathematical equivalence between backward moving particles and forward moving antiparticles is one of Feynman's most elegant insights. It shows that what might look like time travel in a diagram is actually just antimatter moving normally through time. The apparent strangeness dissolves when you understand what the mathematics really describes, and the physical predictions, the actual probabilities of real processes, always respect causality. The mathematics of QED, properly formulated, automatically protects the light cone structure. Feynman didn't add causality as an extra assumption. It emerged from the theory itself. The mathematics of quantum field theory is designed, or perhaps discovered, in such a way that faster than light signaling is impossible. Every process that might seem to allow it, when calculated properly, turns out to respect the light cone. The theory is internally consistent in a deep way that Feynman found beautiful and profound. Let me give you another way to see why the speed limit is necessary. Think about what it means to send a signal, to communicate information from one place to another. Information is physical. This is one of the great insights of 20th century physics, formalized by Claude Shannon and others. Information isn't some abstract thing floating in a void, separate from the material world. Information requires a physical carrier. Something has to move from sender to receiver carrying the information. This might be a photon carrying a pulse of light in a fiber optic cable. It might be a sound wave carrying the vibrations of speech through air. It might be a letter carried by mail, ink patterns on paper transported by vehicles and people. It might be an electron moving through a wire, carrying an electrical signal. It might be a neurotransmitter crossing a synapse in your brain. Whatever the carrier is, it has to travel through space and time. Information doesn't teleport. It moves from place to place, carried by something physical. Now, the speed of light is the fastest that any physical thing can travel through space. Photons travel at this speed. Other massless particles like gluons travel at this speed. Everything else, everything with mass, travels slower. Even particles moving at 99.9999% of light speed are still below the limit. This means the speed of light is the fastest that information can travel. It's not just the speed of one particular thing called light. It's the ultimate speed limit for any physical process. And information transfer is a physical process, but here's the deep point. If information could travel faster than light, it could outrun causality. It could cross the light cone, connecting events that shouldn't be connectable. Effects could precede causes. The future could influence the past. And this leads to the contradictions we've discussed at length. Therefore, the speed limit for information must be the same as the boundary of the light cone. There can't be any way, any trick, any clever scheme to send information faster than light. Because if there were, causality would break, paradoxes would become possible, and the universe would become logically incoherent. The only way to ensure this is for the speed of light to be the ultimate speed limit for everything. Not just light, not just electromagnetic phenomena. Everything. Every force, every particle, every interaction, every possible way of influencing distant events. Feynman explored this deeply in his work on quantum electrodynamics. Photons, the carriers of electromagnetic information, travel at exactly the speed of light. This isn't arbitrary. Photons are massless, and massless particles necessarily travel at the speed of light. They can't go faster, and they can't go slower. Light speed is the only speed available to them. But more deeply, the speed at which photons travel is the speed at which electromagnetic causality propagates. When you jiggle an electric charge here, the effect on distant charges doesn't happen immediately. The change in the electric field propagates outward at the speed of light, like ripples spreading across a pond. Distant charges don't know you've jiggled anything until those ripples reach them. This is actually what Michael Faraday intuited in the 1830s, and James Clerk Maxwell proved mathematically in the 1860s. Changes in electromagnetic fields propagate as waves at a definite speed. That speed turned out to be the speed of light, revealing that light itself is electromagnetic waves. Einstein took this seriously, more seriously than anyone before him, and built special relativity on the constancy of this speed. And Feynman, working out quantum electrodynamics, showed that this structure is preserved at the quantum level. The same is true for all the fundamental forces. In the standard model of particle physics, forces are carried by particles called gauge bosons. The electromagnetic force is carried by photons. The weak nuclear force, responsible for certain kinds of radioactive decay, is carried by W and Z bosons. The strong nuclear force, which holds quarks together inside protons and neutrons, is carried by gluons. Gravity, if we could successfully describe it in quantum terms, would presumably be carried by particles called gravitons. All these force carriers respect the speed limit. Photons travel at exactly light speed. Gluons, though they're never observed in isolation, also travel at light speed. W and Z bosons have mass, so they travel slower than light. Gravitational waves, detected for the first time in 2015, travel at exactly the speed of light, as general relativity predicts. This universality is crucial. It means that no force can act instantaneously at a distance. Newton thought gravity acted instantly. If the sun suddenly disappeared, Newton's theory said Earth would immediately fly off in a straight line, with no delay for the information about the sun's disappearance to reach us. But Einstein showed this was wrong. Gravity propagates at the speed of light. If the sun vanished, we wouldn't know for about 8 minutes, the time it takes light and gravity alike to cross the Earth-Sun distance. The gravitational effect and the last rays of sunlight would reach us at the same moment. Even in the strange, probabilistic world of quantum mechanics, causality is protected. This brings us to one of the most subtle and often misunderstood aspects of quantum physics: the question of quantum entanglement. When two particles become entangled, they develop correlations that persist even when the particles are separated by large distances. These correlations are unlike anything in classical physics. They're stronger, stranger, and they seem to connect distant events in spooky ways, to use Einstein's famous phrase. Here's how it works. You create two particles in a special state, an entangled state, where certain properties of the particles are correlated. For example, you might create two photons whose polarizations are correlated. You don't know what polarization either photon has, but you know that if you measure one and find it vertically polarized, the other will also be vertically polarized. If you find one horizontally polarized, the other will be horizontal too. Now you separate the photons. You send one to Alice in New York and one to Bob in Tokyo. They're thousands of kilometers apart. Then Alice measures her photon's polarization. She finds it's vertical. Instantly, she knows Bob's photon is also vertical. Before Bob measures, before any signal could possibly travel from Alice to Bob, the outcome of Bob's measurement is determined. This seems like faster-than-light communication. Alice does something in New York, and instantly something is determined in Tokyo. Information about Alice's measurement result seems to leap across the Pacific in no time at all. Einstein was troubled by this. He called it spooky action at a distance, and believed it showed something was wrong with quantum mechanics. But Feynman understood why this doesn't actually violate causality. Entanglement involves correlations, not signals. When Alice measures her photon, she learned something about Bob's photon, but she hasn't sent any information to Bob or to anyone near Bob. She's just learned about correlations that were established when the photons were created together. Think of it this way. Suppose you and a friend each take one glove from a pair without looking. You put them in boxes and separate. You go to New York, your friend goes to Tokyo. Then you open your box and discover you have the left glove. Instantly, you know your friend has the right glove. But no information traveled between you, no signal passed. You simply learned about existing correlations that were established when you divided the gloves. The quantum case is stranger because the correlations can't be explained by pre-existing properties. Before measurement, neither photon has a definite polarization. It's not that you just don't know the polarization. According to quantum mechanics, the polarization literally doesn't exist until measured. This is the content of Bell's theorem and the experiments that confirmed it, earning the 2022 Nobel Prize in Physics. But even these strange quantum correlations cannot be used to send information faster than light. Here's why. The measurement results are random. Alice can't control whether her photon will be vertical or horizontal. She just measures and gets a random result. She learns what Bob will find, but she can't choose what Bob will find. She can't encode a message in the correlations because she can't control the correlations. Bob, for his part, just sees random results. Half the time vertical, half the time horizontal, with no pattern. Without knowing what Alice measured and when, he can't extract any information from his results. Only when Alice and Bob get together and compare the results do the correlations become apparent. And that comparison requires classical communication, limited to light speed. Feynman was very careful about this point. Quantum mechanics does not violate causality. The strange correlations of entanglement are consistent with the light cone structure. They're a feature of quantum mechanics, remarkable and counterintuitive, but not a violation of the speed limit. Information still propagates at or below the speed of light. Causality is still protected. And this brings us back to the deep lesson that Feynman uncovered through his decades of work on fundamental physics. The speed of light isn't just a property of light, some contingent fact about electromagnetic radiation. It's the speed of causality. It's the boundary between events that can influence each other and events that cannot. It's built into the structure of space-time, protected by the mathematics of quantum field theory, and necessary for the universe to be logically coherent. The speed of light is the rate at which the universe unfolds. It's the tempo of reality. It sets the pace at which causes can produce effects, at which the future can emerge from the past, at which anything can happen as a consequence of anything else. Feynman saw all of this. Through his diagrams, his calculations, his physical intuition, he saw how the pieces fit together. He saw that the speed limit isn't a limitation imposed on an otherwise unlimited universe. It's a feature that makes the universe possible. It's what allows cause and effect to work. It's what allows history to be consistent. It's what makes physics work at all. Without this speed limit, without the light cone structure it creates, the universe couldn't contain experiments. It couldn't support science. It couldn't have observers making observations that mean anything. Every observation would be contaminated by influences from the future. Every experiment would be undermined by effects that precede their causes. Nothing would be predictable because the past wouldn't be fixed. The speed of light makes paradox impossible. It ensures that every cause precedes its effect, that every action has forward-flowing consequences, that logic itself remains intact. Without this limit, you could receive messages from tomorrow, warnings about decisions you haven't made, information that contradicts itself. Reality would dissolve into incoherence. The speed limit isn't a barrier to what we might achieve. It's the wall that keeps chaos out. This is what Feynman uncovered. This is why the speed of light is the limit. Not because we can't build fast enough rockets, not because we don't have enough energy, but because exceeding it would break the logical structure of the universe itself. The limit is what holds reality together. We've explored what the speed of light is and how scientists discovered it had a finite value. We've seen how Einstein revealed its fundamental role in the structure of space-time. We've understood what Feynman uncovered about its intimate connection to causality. And we've examined why exceeding it would break logic itself, creating paradoxes that would make reality incoherent. Now let's go even deeper. What does this speed limit mean for the universe as a whole? What does it tell us about the nature of reality at its most fundamental level? And what are the practical and philosophical implications of living in a cosmos where causality has a speed, where cause and effect unfold at a finite rate across the vast distances of space? First, let's address a question you might be wondering about. Why does the speed of light have the particular value it has? Why 299,792.458 kilometers per second and not some other number? Why not an even 300,000? Why not a million? Why not 10? The short answer is that the question is somewhat meaningless, at least in the way it's usually asked. The speed of light has that particular numerical value because of how we define our units of distance and time. We invented meters. We invented seconds. The speed of light existed before we did. When we measure it using our invented units, we get a number, but that number depends on our choices. If we measure distances in miles instead of kilometers, we get a different number, about 186,000 miles per second. If we used feet, we get yet another number, about 983 million feet per second. The physical reality hasn't changed. Only our description of it has. What matters physically is not the number itself, but the relationships that the speed of light creates. How does it compare to other speeds? How does it connect space and time? How does it interact with other fundamental constants? These relationships are what physics actually describes. Consider this thought experiment. If the speed of light were twice as fast in our units, what would change about physics itself? Actually, nothing fundamental would change. The relationships between space, time, energy, and matter would be exactly the same. We just use different numbers to describe them. It's like asking why there are 100 centimeters in a meter. The answer is that we defined it that way. The physical reality of distances doesn't depend on our arbitrary choice of units. In fact, physicists often use systems of units where the speed of light equals exactly 1. In these natural units, you measure distances and times in the same units. A light year becomes simply a year. The equations of physics become simpler and more elegant. The speed of light disappears from the formulas, not because it's unimportant, but because it's been absorbed into the very definition of how we measure things. But there's something deeper here, something that does matter physically. What is meaningful is how the speed of light compares to other constants of nature. And this leads to some of the deepest and most troubling questions in all of physics. There's a number called the fine structure constant. It's approximately 1 divided by 137, or more precisely, 0.007299735. This number describes the strength of the electromagnetic force, how strongly charged particles interact with each other and with light. The fine structure constant is special because it's dimensionless. It's a pure number with no units attached. It's the same whether you measure things in meters or miles, seconds or hours, kilograms or pounds. It doesn't depend on your choice of units at all. It's a fundamental ratio built into nature itself. The fine structure constant involves the speed of light in its definition. It's constructed from the electron charge squared, divided by the product of Planck's constant, the speed of light, and a constant related to the permittivity of empty space. All these fundamental constants combine to produce this pure number, approximately 1/137. The fact that this dimensionless number has the value it has, rather than some other value, is not something we can derive from more fundamental principles. We can measure it with extraordinary precision. We use it in calculations constantly, but we cannot explain why it has this particular value. It appears to be a brute fact about our universe, something that simply is, without deeper explanation. Feynman was fascinated and troubled by the fine structure constant. He famously said that all good theoretical physicists put this number up on their wall and worry about it. It's a magic number that comes to us with no understanding. We don't know what kind of dance to do on the computer to make this number come out, he said. We don't know what wheels to turn. This mystery haunted Feynman throughout his career. Here was a number at the heart of his greatest achievement, quantum electrodynamics, and he couldn't explain where it came from. He could use it to make predictions of astonishing accuracy, but he couldn't derive it from anything more fundamental. If the fine structure constant were different, the universe would be different. If it were much larger, electromagnetic forces would be stronger, atoms would behave differently, the energy levels of electrons would shift, chemistry as we know it might not work, molecules might not form in the ways they do. Life, if it could exist at all, would be radically different. If the fine structure constant were much smaller, electromagnetic forces would be weaker. Again, chemistry would change, Stars might burn differently. The delicate balance that allows complex structures to form might be disrupted. The same is true for the speed of light in relation to other constants. The relationships between the fundamental constants determine what kinds of structures can exist in the universe. They determine what kinds of chemistry is possible, what kinds of stars can form, what kinds of planets can exist, what kinds of life might evolve. We seem to live in a universe where these constants are tuned to allow complexity. The electromagnetic force is strong enough to hold atoms together, but not so strong that atoms collapse. Gravity is weak enough that stars can burn for billions of years, giving life time to evolve, but strong enough that stars and galaxies can form in the first place. The nuclear forces are balanced to allow hydrogen to fuse into helium, powering stars while leaving some hydrogen unfused, providing the raw material for chemistry. This observation has led some physicists and philosophers to discuss what's called the anthropic principle. The idea is that we shouldn't be surprised to find ourselves in a universe compatible with our existence, because we couldn't exist in an incompatible universe. If the constants were different, if physics didn't allow complex chemistry and long-lived stars and stable planets, we wouldn't be here to ask questions about it. We'd never have evolved. This doesn't explain why the constants have the values they do. It just explains why we observe those particular values. It's a selection effect. Out of all possible universes that might exist, we necessarily find ourselves in one that allows observers like us. We can't observe universes where we couldn't exist. Feynman was skeptical of anthropic reasoning. He found it unsatisfying. It feels like giving up, like saying we can't explain it, so we'll just note that it had to be this way for us to be here asking. Feynman preferred to seek explanations from deeper physics, from more fundamental theories that might predict the values of constants rather than just accepting them. But he acknowledged that the values of fundamental constants remain mysterious. The speed of light is one piece of this mystery. We know it's fundamental, we know it's necessary for causality, we know it connects space and time, but we don't know why it has exactly the value it does in relation to everything else. That remains an open question, perhaps the deepest open question in physics. Now let's talk about what Feynman's work on quantum electrodynamics revealed about the role of the speed of light in the deeper structure of physical law. In QED, the speed of light appears everywhere. It's not just a constant that shows up occasionally. It's woven into the fabric of the theory at every level. It appears in the equations describing how electrons interact with photons. It appears in the propagators, the mathematical functions that describe how particles travel from one point to another through space-time. It appears in the coupling constant, the fine structure constant we just discussed. It's inescapable. What Feynman showed through his diagrams and calculations is that QED is remarkably consistent. Despite all the strange features of quantum mechanics, the probabilistic outcomes, the wave-particle duality, the uncertainty principle, the weird superpositions and entanglements, everything hangs together. The theory doesn't contradict itself. Causality is preserved. And predictions match experiments to extraordinary precision. Remember the extraordinary precision we discussed earlier. QED's prediction of the electron's magnetic moment matching experiment to more than 10 decimal places. This precision isn't accidental. It's built on the speed of light being a constant, unchanging feature of space-time. If the speed of light varied, if it were different in different places or at different times, the whole structure of QED would collapse. The theory would become inconsistent. Those precise predictions would fail. The fact that QED works so well, that reality matches the mathematics so precisely, is powerful evidence that the speed of light really is constant, really is fundamental, really is built into the structure of reality exactly as special relativity claims. The fact that QED works so well, that its predictions match reality so precisely, is powerful evidence that the speed of light really is constant, really is fundamental, really is built into the structure of reality in exactly the way special relativity claims. Remember, Feynman's path integral formulation, where particles explore all possible paths through space-time simultaneously. You might expect that faster-than-light paths would contribute to these sums. After all, we're including every conceivable trajectory. But here's what the mathematics reveals. When you work out the path integrals with proper attention to relativistic quantum field theory, the contributions from faster-than-light paths cancel out or become exponentially suppressed. The causal paths dominate. The acausal paths contribute nothing to physical reality. Feynman didn't impose this as a rule. It emerges from the mathematics itself. The structure of quantum field theory, built on special relativity, automatically enforces the speed limit. Any attempt to construct a theory that violates causality produces inconsistencies, infinities that can't be tamed, probabilities that don't make sense. The consistent theories, the ones that actually describe reality, are exactly those that respect the light cone. This gives us deep confidence that the speed limit isn't just an empirical observation, something we've noticed but might be violated in exotic circumstances. It's a feature of the theoretical framework that describes our universe at its most fundamental level. The math itself enforces causality. If you try to build a quantum field, theory that violates causality, that allows faster-than-light propagation of information, the theory becomes inconsistent. It produces contradictions. It generates infinities that can't be renormalized using Feynman's techniques. It makes predictions that don't make sense, probabilities greater than 1 or less than 0, amplitudes that blow up to infinity. The consistent theories, the ones that hang together mathematically, are exactly the ones that respect the speed of light. This is a powerful hint, perhaps more than a hint, that the speed limit isn't accidental. It's necessary. It's built into the logical structure of any coherent description of reality. Let's shift now to thinking about what the speed limit means practically for our existence in this universe, because the implications are profound, affecting everything from our ability to explore the cosmos to our understanding of our place within it. The speed of light is fast by human standards, unimaginably fast. Nothing in our everyday experience moves anywhere near that speed. The fastest human-made object, the Parker Solar Probe at its closest approach to the Sun, reaches speeds of nearly 200 kilometers per second. That's about 1/1800th of the speed of light. Even that incredible speed, fast enough to cross the United States in less than a minute, is a tiny fraction of light speed. But the speed of light is not fast compared to the distances of space. And this is where the limit becomes practically significant for our civilization and our future. We established earlier that sunlight takes about 8 minutes to reach Earth. But consider what this really means. If the sun suddenly went dark, you wouldn't know for 8 minutes. The last photons it emitted would still be traveling toward you, carrying the final message of a star that no longer exists. For 8 minutes, you'd live in a universe where the sun still shone even though it didn't. The present moment at the sun and the present moment on Earth are causally disconnected, separated by 8 light minutes of space-time. Light from the nearest star beyond our sun, Proxima Centauri, takes about 4.24 years to reach Earth. When you look at Proxima Centauri, you're seeing it as it was during a different presidential administration, a different phase of your life, a different moment in history. Any message we sent there, traveling at light speed, would take over 4 years to arrive. A reply would take another 4 years to return. A simple exchange of hellos would span most of a decade. Light from the center of our own galaxy takes about 26,000 years to reach us. We see the galactic core as it was when humans were painting on cave walls, before agriculture, before writing, before civilization as we know it. Whatever is happening there now, we won't know for 260 centuries. Light from the Andromeda Galaxy, our nearest large galactic neighbor, takes about 2.5 million years to reach us. We see Andromeda as it was when our ancestors were just beginning to walk upright on the African savanna. The light that enters your eye tonight left Andromeda before the genus Homo even existed. And the most distant objects we can see, galaxies near the edge of the observable universe, are so far away that their light has been traveling for over 13 billion years. We see them as they were when the universe was young, when the first stars were forming, when the cosmos was a very different place. These light travel times create a fundamental limit on how quickly we can communicate across space, how quickly we can receive information from distant events, how quickly we could ever travel to distant destinations. The speed of light is the maximum speed at which we can gather information about the universe, the maximum speed at which we can influence distant events. When we look at the Andromeda Galaxy, we see it as it was 2.5 million years ago. If something dramatic happened there last year, a supernova, a collision, a gamma ray burst, we won't know for another 2.5 million years, -1. The information is traveling toward us at light speed, but it has an immense distance to cover. We're looking at ancient history, not current events. This is true for everything we observe in the cosmos. Everything you see has already happened by the time the light reaches your eyes. The farther away something is, the further into its past you're looking. The observable universe is a sphere of ancient light, showing us the history of cosmic evolution from the distant past to more recent times as we look closer to home. For space travel, the implications are even more profound and limiting. The nearest star is 4.24 light-years away. Even traveling at an incredible 10% of light speed, which is vastly beyond our current capabilities, reaching Proxima Centauri would take over 40 years. A round trip would take nearly a century, assuming no time spent at the destination. If you wanted to travel to Proxima Centauri and return within a human lifetime, you'd have to travel at a substantial fraction of light speed. And here at least, relativity offers some comfort. Time dilation would help. If you traveled at 90% of light speed, time would pass more slowly for you than for people on Earth. Your trip might feel like a few years to you while decades passed on Earth. You could return still young while everyone you knew had aged dramatically. But this creates its own strangeness. You'd return to a world that had moved on without you. Friends and family would be old or dead. Technology would have advanced. Culture would have changed. You'd be a visitor from the past, preserved by relativistic time dilation while the world aged around you. And no matter how fast you traveled, you could never get information home faster than light. Even if you discovered something wonderful at Proxima, Centauri, a habitable planet, signs of life, resources worth harvesting, your message back to Earth would take 4.24 years to arrive. And any response from Earth would take another 4.24 years to reach you. Communication across interstellar distances is fundamentally slow, limited by the speed of causality. This has led some to speculate about whether advanced civilizations might find ways around the speed limit. Perhaps wormholes, hypothetical tunnels through space-time predicted by general relativity could provide shortcuts. You'd enter a wormhole here and emerge light years away, having traveled a shorter path through higher dimensional space. Perhaps the expansion of space itself, which can carry galaxies apart faster than light, could somehow be harnessed for travel. But all the serious physics points to these ideas being impossible, or at least not allowing faster than light communication or travel in any useful sense. Wormholes, if they exist at all, would likely be incredibly unstable. Any attempt to send something through might cause them to collapse. Keeping a wormhole open long enough to travel through might require exotic matter with negative energy density. Matter that may not exist and may not be possible. And even if you could somehow stabilize a wormhole, the same causality arguments we've explored suggest you couldn't use it to send information faster than light without creating paradoxes. The expansion of space is often cited as an example of faster than light motion, and in a sense it is. Distant galaxies are receding from us faster than light because the space between us and them is expanding. But this doesn't violate the speed limit because nothing is actually traveling faster than light through space. Space itself is expanding, carrying galaxies along. You can't use space expansion to send a message or to travel anywhere faster than light. The speed of light appears to be an absolute barrier, a fundamental limit that shapes what's possible in this universe. We may be confined forever to exploring our local region of space, a few hundred or thousand light years around the sun. We may never visit distant galaxies. We may never communicate in real time with beings more than a few light years away, if such beings exist. This is humbling. It means the universe is vast and largely unreachable. Most of the cosmos is forever beyond our grasp, not because we lack ambition or technology, but because the structure of space-time itself prevents access. The light we see from distant galaxies is ancient history by the time it arrives. The cosmos is full of events happening right now that we won't know about for millions or billions of years. But there's also something beautiful in this structure. The speed of light creates layers of history visible in every direction. By looking out into space, we look back in time. The deeper we look, the further back we see. The cosmic microwave background radiation, the afterglow of the Big Bang, shows us the universe as it was 380,000 years after its birth, almost 14 billion years ago. The universe is a time machine, not one that lets us travel to the past, but one that lets us see the past. Every telescope is a window into history. Every observation of a distant star or galaxy is an archaeological expedition into cosmic antiquity. The light that reaches our instruments carries information about conditions that existed long before Earth formed, long before our solar system existed, long before the Milky Way took its current shape. And the speed of light is what makes this possible. If light traveled infinitely fast, we'd see everything as it is right now. The universe would have no visible history. Every observation would show the present moment everywhere. There would be no layers of time, no cosmic archaeology, no window into the past. But because light takes time to travel, because the speed of causality is finite, the universe reveals its past to us in layers of deepening history. Look at the moon, and you see 1.3 seconds into the past. Look at the sun, and you see 8 minutes into the past. Look at distant stars, and you see years or centuries into the past. Look at distant galaxies, and you see millions or billions of years into the past. Feynman appreciated this aspect of physics, the way the mathematical structure of the universe creates beauty as well as constraint. The speed limit isn't just a barrier to our ambitions. It's part of what makes the cosmos intelligible. It's part of what allows us to do science, to understand where we came from, to trace the evolution of the universe from the Big Bang to the present day. Let me return to what I consider the deepest insight Feynman brought to this subject. It's about why the universe can exist at all with a structure we can understand. Causality is fundamental. Effects follow from causes. The future flows from the past. Without this, there's no science. Without this, there's no prediction. Without this, there's no understanding, no meaning to events, no coherent concept of explanation. If the future could cause the past, if effects could precede causes, the whole notion of explanation would collapse into incoherence. The speed of light is what protects causality. The light cone divides space-time into regions that can and cannot influence each other. This division ensures that causes precede effects for all observers in all reference frames. This structure makes the universe logically coherent. Feynman saw that the speed limit isn't a limitation on our abilities, something that holds us back from achieving what we might otherwise achieve. It's a feature of reality that makes reality possible. A universe without this speed limit would be a universe without consistent cause and effect. It would be a universe where logic itself fails. This is why the speed of light is properly called the speed of causality. It's not just how fast light happens to move, it's how fast causes can produce effects. It's the rate at which the universe unfolds, the tempo at which reality progresses from moment to moment. And here's something even more profound that emerges from this understanding. The speed of light connects space and time. It's the conversion factor between them. In the space-time interval formula, we multiply time by c to compare it with space. In Einstein's famous equation relating energy and mass, E equals mc squared, the speed of light squared converts mass into energy. The speed of light is the bridge between dimensions that seem utterly different. Space is something you can move through in any direction. Forward, backward, left, right, up, down. Time is something that flows inexorably forward, something you can't control, something that carries you along whether you want to go or not. They seem like completely different kinds of things, but special relativity reveals they're not different. They're aspects of a single unified space-time. The speed of light is what relates them, what converts between them, what makes it possible to describe them with the same mathematics. Time is just another dimension, woven together with space into a four-dimensional fabric. The speed of light is what makes this weaving coherent. This unity of space and time is one of the great discoveries of 20th century physics, and at its heart sits the speed of light, the constant that makes space-time work as a coherent structure. Feynman spent his career exploring the consequences of this structure. His diagrams, his path integrals, his renormalization techniques all work within the framework that the speed of light provides. and all confirm that this framework is consistent, precise, and beautiful. The mathematics hangs together. The predictions match reality. The structure is sound. If you ask what Feynman uncovered that will break your brain, it's this. The speed of light is not about light. It's about reality itself. It's the speed at which causes produce effects. It's the speed at which the future emerges from the past. It's the speed at which the universe unfolds, moment by moment, event by event. It's woven into the very fabric of space-time. It's enforced by the mathematics of quantum field theory. It's necessary for logic and coherence and existence itself. You cannot exceed the speed of light, not because something would stop you, not because you run out of fuel or hit a wall. You cannot exceed it because exceeding it is a logical impossibility. It's like being in two places at once or making 2 + 2 = 5. The question of what it would be like to go faster than light has no answer, because the question doesn't make sense. It's asking what it's like to do something that can't be done. And this isn't a failure or a frustration. It's a revelation about the nature of existence. We live in a universe with structure, with rules, with a logical fabric that holds everything together. The speed of light is part of that fabric. It's what allows the universe to be a place where things happen in an orderly way, where causes lead to effects, where the past shapes the future, where your decisions actually matter. The next time you turn on a light and see a room illuminate instantly, remember what you're witnessing. Light is traveling at the universe's fundamental speed limit, the speed of causality. It seems instant only because the distances are small. Over the vast gulfs of space, light's finite speed becomes apparent. The next time you think about the future, about planning and hoping and fearing what's to come, remember that this orientation toward the future is protected by the speed of light. Causality gives meaning to your choices, and causality has a speed. Richard Feynman understood physics as few others have. He saw through equations to physical reality. He thought in pictures that revealed deep truths. And what he saw at the heart of it all was a universe structured around causality. The universe is vast and old. We're tiny creatures on a small planet around an ordinary star. We've existed for a cosmic eye blink. But in that brief existence, we figured out remarkable things. We've understood the structure of space-time. We've discovered the relationship between space and time. We've seen why the speed of light must be what it is. This is what Feynman uncovered. The speed of light is the speed of causality. It's what makes the universe possible. It's what allows cause to lead to effect, past to lead to future, reality to cohere. That band of light from distant stars, the signals in your phone, the glow of everything you see, all of it travels at this universal limit. All of it participates in the causal structure of existence. All of it unfolds at the tempo set by space-time itself. The speed of light isn't just fast, it's necessary. It's the heartbeat of causality, the rhythm of reality, the foundation of existence. Feynman once said that nature uses only the longest threads to weave her patterns. So each small piece of a fabric reveals the organization of the entire tapestry. The speed of light is one of those threads. Pull on it, and you find it connected to everything. To space and time, to cause and effect, to energy and mass, to the logical coherence of existence itself. We live in a universe where the future genuinely flows from the past, where your choices genuinely matter, where causes genuinely produce effects. This isn't guaranteed. It's protected. protected by the geometry of space-time, protected by the speed of causality, protected by the limit that Feynman helped us understand. And once you understand that, nothing looks the same. Thank you for joining me on this exploration of one of the deepest ideas in physics. If you found it fascinating, if your mind is a little bent from contemplating the speed of causality, please consider liking this video and subscribing. Your support helps me continue these deep dives into the nature of reality. The universe is full of mysteries. The speed of light is one of them, hiding in plain sight. Now you know what it really is. Not just how fast light travels, but what makes the universe possible. Sleep well tonight, knowing that causality holds the cosmos together. The speed of light is the limit, and Feynman showed us why that limit is what makes everything work. Good night.